Welcome guys, on this tutorial we are building NØNOS, a privacy first operating system entirely from scratch. What you are about to see today is not Linux, not BSD, not based on any existing kernel. This is over 300,000 lines of Rust code entirely from the ground up, with one goal: cryptographic trust at every layer of the system. So today I wanted to build the system from scratch and walking through exactly what happens when NØNOS is booting. So the main time we just use our make file. So I run make run to build the bootloader and the kernel. I already cleaned the previous build artifacts and targets directories, and now we just run make run, and we are building first the bootloader. So this is a separate directory inside from the kernel. So the bootloader is on its own, is a UEFI application. So what this means, this is a UEFI application written in Rust, and unlike traditional BIOS bootloaders, UEFI gives us a modern 64-bit environment with access to firmware services, graphics, and most importantly, a secure boot chance integration. At second, we have the kernel. This is the heart of NØNOS. It's a no-standard Rust binary, meaning it doesn't use any standard library, no libc, no POSIX, and every system call, like every driver, like every memory allocator, is implemented from scratch. Then we have a feature which is unique on its own, the Zika proof generator. This creates a Growth 16 zero knowledge proof that cryptographically attests to the integrity of our kernel. So it's added security feature. We'll see this in action during the boot. So now we are building the kernel. From the bootloader we have just two warnings. I will fix them before public release. The kernel we have a few warnings as well, but it's good because it's coming all together, is not public released yet, and it will take another 2 to 3 weeks to make it clean, to fix some of the issues, etc. So now we are building the kernel. As you can see, the bootloader and the kernel have a signature key. By default, NØNOS uses AD25519 for code signatures, which is the same elliptic curve cryptography used by Signal, or by another example, the Tor network. It uses AD25519 signatures. So the bootloader contains the public key. The kernel is signed with both the public and private key during boot. The bootloader verifies the signature before transferring control. So this means even if attacker modifies the kernel binary on disk, the system refuses to boot. So it's another security feature we added. We further and power this by adding a Zika proofs attestation. So let's see, it's almost about to finish. There are a few warnings to fix. There were a lot of changes as well during build phase last month, from October, November, December. So we definitely improve it for the best, and now it's about ensuring everything will be clean and stable for a public release, but preparing a tutorial to show what is going on. I have nothing to hide, and so yeah. So now let's wait it to finish. Okay, about the Zika snark attestation. Here where NØNOS diverges from every other operating system. We generate basically a growth 16 zero knowledge proof, but what does this prove? It proves that the kernel binary hashes to a specific value that hash was signed by your key, and signature is valid, all without revealing the private key or requiring trust in any third party. So the proof itself is only 192 bytes, but verifying it requires the bootloader to perform elliptic curve pairings over BN 254 curve. So this is real cryptography running in the bootloader at the bootloader level before the kernel even loads. So why does this matter? Because the proof can be verified by anyone, anywhere, without access to our signing infrastructure. It's a cryptographic proof of kernel integrity that doesn't require trusting us, only trusting mathematics and code. So before any public relays, this is our work. 2 bootloader warnings, 458 on the kernel side. So here are the signing key I show you later. So now let's go here. The NØNOS bootloader initializes in UEFI mode. First it sets the graphics output protocol. That's how we're reading this boot screen directly from the bootloader before any kernel code runs. Then we have a cryptographic verification sequence with signature, etc. So as well Zika proofs, and then we jump to the operating system. Let's see what happened. We can see this from the terminal as well. So first, it is our kernel, 6.2 megabyte size. We have our public key, this one. We have our signature key, and the kernel is signed successfully. So then it happens the Zika proof generator. So we have our own tools. It comes from our tools. Yes, from the bootloader tools, attestation circuits, and then we just generating a proof. This is our command. Then we load loading probing key, which is this byte size. The program hash is here, capsule commitment is here, and hardware attestation level we have. The proof generation is complete, the capsule commitment, proof size, and Zika proof generated successfully. Then we have the embedding tools, which will embed these compiled Zika proofs, circuits generated to the bootloader site. The proof file size, as we said, is 192 bytes. The public inputs is only 128 bytes for field elements. Then we have a program hash provided, capsule commitment on this embed stage as well. The Zika proof block size is 400 bytes. Then we have here our Zika block header, etc. So what we seen before in the booting is basically this, which we verified the signature first and the growth Zika proof at last stage before loading the kernel. We can see it. You can see it here. So we load the bootloader. This is what happens as soon as QEMU starts. So we are booting, UEFI servers initializes UEFI modes. Then we set up first the graphics, output protocol, and how we're driving this boot screen directly from the bootloader before any kernel code runs. Then we have the signatures. You can see everything. So everything is verifiable. All the code, all the mappings, etc. Then we have here, etc. This was a small tutorial to show if we are alive, we are working, and before any public release we are just making sure to have the best outcome possible. And thank you everyone if you took your time to see this. I hope I shared some value, and let's crack it up and let's make it happen. I'm really excited about the future. We are working really hard and more tutorials to follow, but thank you to everyone to be part of this journey, and I wish a wonderful day. Bye.